Yes, ma'am.
Sorry. Okay. We will have the discussion session once I'm done with all the 10 questions. Like in between, just like you guys note down the questions that you guys have. Okay. Yeah. We are going to see tutorial 3 of BT39 Bioreactors course. So here, the first question is, an industrially important enzyme is produced from the thermophilic bacteria in a bioreactor operated in batch mode. 70 liters of media was inoculated using 8 gram of cells. The lag phase was found to be 30 minutes. The maximum specific growth rate of the organism is 0.52 R inverse under the conditions maintained. Calculate the cell concentration after ninth hour of growth. Choose the answer closest to your calculated answer. So, as per problem solving, what we have to do at first, we have to write what are all the given data. So, what they have given here, just a minute, I'll take the laser pointer. Yeah, what they have given here is 70 liter of media was inoculated using 8 gram of cells. So, from this, what we can calculate, x naught is equal to 8 gram cells in almost like 70 liter of media, which gives us 0.11 gram per liter of cells. That's your x naught, right? And t naught is the lag time, which is almost 30 minutes. So we have to use everything in the same unit, right? So I have just changed it to hours. And the maximum specific growth rate mu max has been given as 0.52 R inverse, and it's what we have to find is that the cell concentration after 9 hours. So here our T will be 9 hours, and then what we have to find here is the cell concentration, that is X, after 9th hour. This is what we have to find. So we have written the given data as well as what we have to find from this problem. So we very well know what's the equation that we have to employ for this problem to be solved, which is 1 by mu ln of x by x naught plus t naught is equal to t. So we already know what is our mu max, and we just assume that mu is equal to mu max here, and x and x naught has been given. Sorry, x we have to find, x naught we have like derived from the problem statement. T naught we know that is 9 hours, and T naught is 0.5 hours, and T we know which is 9 hours. By substituting the given data in the problem, we are just trying to solve it. Okay, so first what we have to do, we have to take 0.5 to the right hand side, which gives almost 8.5. So what is left out now? 1 by 0.52, which will go here as multiplication. So by multiplying 8.5 into 0.52, we get 4.42. So here, if the ln is going from left side to the right side, what it becomes? Exponential, right? So by taking exponential of e power 4.42, we get like 83.1. So here by multiplying 0.11 to 83.1, we get x is equal to 9.2. So the closest answer out of these four options will be 9.5 gram per liter. So here the answer is 9.5 gram per liter. Moving on to question 2. In a chemostat containing suspended cells, if you guys have any doubt in question 1 or whatever the questions that are being solved here, kindly note it down. We'll definitely discuss once the 10 questions are over. Okay. Question number 2. In a chemostat containing suspended cells operating at steady state with negligible death rate, which of the following statements is bar or valid? So it can be either one or more than one. Okay. So what they have given, the specific growth rate of cells is equal to the dilution rate. The specific growth rate of cells is greater than the dilution rate. Specific growth rate of cells is lesser than the dilution rate. The specific growth rate is unaffected by the dilution rate. So we'll just see, like in chemostat what happens, there will be a continuous inlet as well as there will be a continuous outlet. Sorry, here the arrow mark is wrong. It should not be here. It's being taken away, right? So So the inlet feed rate will be Fi, and inlet substrate concentration will be Si, and the what to say, like your inlet cell concentration will be Xi. Similarly, if you see the outlet feed rate is designated as F, the outlet substrate concentration is S, and the outlet cell concentration is X. Okay, so we'll write the overall mass balance here, especially the mass balance on cells. So what is the overall mass balance? Like the normal equation that we use is Ri inlet minus R naught plus Rg, which is the generation, minus Rc, which is the consumption, is equal to the rate of accumulation. So what they have clearly given here is that it is being operated at steady state with negligible death rate. Okay, so what does it mean? Your accumulation, as they are telling, it's going to be operating at steady state, this will become 0, and with a negligible death rate, which means there is no consumption, right? So these two are going to get 0, and we already know there are no inlet which is giving you any cells in chemostat. It's just only the cells that are coming at the outlet. So if you substitute all these, we get R minus R naught plus Rg is equal to 0, right? Taking R naught to the right hand side, Rg is equal to R naught. So what is Rg? Generation, and R naught is the rate of cells that are going to the outlet, right? So here generation designates mu into X, that is the specific growth rate, into the cell concentration for the total volume, which is V, which is equivalent to R naught is nothing but your outlet concentration into the feed rate that is being used. Okay, flow rate that is being used, not feed rate, sorry, the flow rate that is being used. So by like rearranging the formula, we get rearranging the equation, we get F by V minus mu into X is equal to 0, and we already know that F by V is the dilution rate, which means D minus mu into X is equal to 0, right? Which means if these are going to be 0, we can say X is equal to 0, then mu will become D is equal to D, which is the specific growth rate is equal to the dilution rate, right? So the option A is right out of these 4 options. Here in chemostat containing suspended cells operating at steady state with negligible death rate, the specific growth rate of cells is equal to the dilution rate. Moving on to question 3. If E. coli is grown on a media containing both glucose and lactose, which of the following phenomenon is observed in its growth? Whether it's dioxy growth, immortality, decreased cell growth compared to the use of only lactose as the carbon source, prolonged lag phase. So we all know that if 2 carbon sources are being present, how the growth profile looks like, it's going to be dioxy growth. So what E. coli does is like, it will, as glucose is already available, E. coli will start consuming glucose at first, and once the glucose is, this is the lag phase for glucose, and then the exponential phase will be attained, and once the carbon source, that is the glucose, is over, the organism will start using the second carbon source, which is nothing but lactose. That's why there is one more lag phase where the cells are getting adapted to lactose as the carbon source. Once it gets adapted to the lactose as a carbon source, your second exponential state will start. So this we call it as dioxy growth. So the answer is A, that is dioxy growth. But I want to relate this dioxy growth with something called catabolite repression. So we'll just see like why E. coli consumes glucose at first, why lactose on the second side. Okay, this is very simple because glucose is remaining as glucose, right? Your lactose has to be broken down at first to glucose and galactose, then only the organism can utilize glucose and galactose as carbon source. So the enzyme has to act on lactose to get your glucose for glycolysis. Whereas here glucose is available as such, which will be easier for the organism to utilize. That's why the organism chooses glucose over lactose as the first carbon source for its growth. Okay, So we'll just see what is called catabolite repression here. So this is the lac operon that we are talking about. Lac operon is nothing but it has the inhibitor enzyme, as well as these are the genes that will code for the enzymes which are going to help in metabolizing lactose as a carbenzone. Okay, so what happens at first? The question that is being given is if glucose is grown on a media containing both glucose and lactose. So we'll just consider both glucose and lactose are being present. So if glucose is present, what happens is that if glucose is present in higher quantity, it will reduce the CAMP levels in the cell. So see how it does is that glucose inhibits an enzyme called adenylate cyclase, which converts ATP to CAMP. Okay, ATP will be converted into CAMP. Glucose goes and inhibits this adenylate cyclase. Therefore, CAMP will not be produced from your ATP. Like it will be very less. Okay. So if CAMP level is less, there is this complex called CAMP cap complex. This will be very less. So this complex has to go and bind to the upstream region of your operon, because of which the transcription happens. If this is present in very less concentration, what happens is that either the transcription will not happen at all, or else it will happen in a very lesser, the expression will be very less. The transcription rate will be very less from this. So what happens? The enzymes that are required for metabolizing lactose will be produced in very less quantity. Therefore, the lactose will not be consumed at all. So the second case what we can consider here is that only lactose is present. So if lactose is only present, what happens? The CAMP level will be more, as glucose is not present, or even glucose is present in very less quantity. Your CAMP level will be more, because of which your CAMP cap complex will be more. So what happens? It goes and binds to the upstream region of your operon. Therefore, it will recruit the RNA polymerase complex over here. Therefore, the transcription happens very efficiently. What happens here? The enzymes that are required for metabolizing lactose will be transcribed in very higher quantity. It will be transcribed at higher expression, it will be transcribed at a very higher rate. Therefore, the enzymes will be produced through translation in a very higher expression rate as well. Therefore, your lactose consumption will start happening. So this we call it as catabolite repression. So this has a huge relation or an intense relation with this term called dioxide growth. Okay. Moving on to question 4. At which phase of cell growth is the maximum specific growth rate observed? Either it is lag phase, exponential phase, stationary phase, or production phase. So here, first we have to clarify this production rate can be either exponential phase or your stationary phase, right? We don't know what is going to be your product of interest. If your product is going to be growth associated product, then your production phase will be your exponential phase. If the product is going to be non-growth associated product, then your production phase will be stationary phase one. So this we are not at all clear, as the product has not been given to us. So we'll just see. This is the growth rate of the growth profile of an organism, right? You will have lag phase followed by your exponential phase, and then your stationary phase, and organism finally reaches the death phase, right? This is for viable cell concentration. So in lag phase, what happens? The cells will just try to adapt to the environment in which you have given it, right? So it will just try to adapt to the environment in the media. So in this case, the organism will not have just the organism size will increase, the cell size will increase, but the cell number will not increase at all. If the cell number is not at all getting increased, that's why lag phase is almost plain, right? And similarly, in stationary phase, what we call your cell death as well as cell production are equivalent, right? That's what happens in the cell stationary phase. That's why here also it's a very straight line. Whereas in exponential phase, as the name suggests, that the organism reproduces exponentially. So if your slope is going to be almost constant, then we call here mu is equal to 0, right? There is no change in the organism growth only. Whereas what happens in the growth phase, that is the exponential phase, the organism goes exponentially from 2 to 4, 4 to 8, 8 to 16, like that it grows exponentially, because of which you will get your slope, which will be your mu. So here your maximum specific growth rate will be observed in exponential phase. Okay. Moving on to question 5. What happens if the dilution rate is larger than the critical dilution rate? So what they are asking, what if we know what is dilution rate, which is nothing but D is equal to your flow rate divided by the volume, right? They are asking what if your dilution rate is greater than the critical dilution rate. So we call something as critical dilution only because the continuous process shouldn't be operated above this. That's why it's called critical dilution rate. It shouldn't be operated above this. So if the dilution rate is going to be above the critical dilution rate, what happens? If D is higher than that, your flow rate is going to be very high. If your flow rate from the bioreactor, the outlet is going to be very high, what happens? So much of whatever the cells that are being reproduced also, like it will just keep on coming out and out, and there will not be enough time for the cells that are there inside the bioreactor to reproduce and multiply also. It will be keep on coming outside only. So this phenomenon we call it as washout of cells. So if the dilution rate is greater than the critical dilution rate, then the washout of cell happens. What I'm trying to say is that the flow rate is very high, because of which the organism will not have enough time to stay inside the reactor to multiply, and then to keep the concentration inside the bioreactor at even a critical level also. It will be the biomass will keep on coming in the outlet, because of which completely the cells will be washed out from the chemostat one. So moving on to question 6. Pseudomonas species is cultured in a chemostat for the production of lipases. The chemostat has a capacity of 45 meter cube. Substrate concentration in the continuous feed is 14 gram per liter. Ks for the organism is 0.51 gram per liter. Under the operating condition, the organism has a maximum specific growth rate of 0.36 R inverse. Estimate the feed flow rate required to achieve 90% substrate conversion. Choose the answer closest to your calculated answer. So we'll just write down what are all the given data. So what they have given, the capacity, that is the volume of the bioreactor chemostat, is going to be 45 meter cube. And your inlet substrate concentration, that is SI, is equal to 14 gram per liter. And your Ks monad parameter is going to be Ks is equal to 0.51 gram per liter. The maximum specific growth rate which is given here is 0.36 R inverse. And they have given that you have to achieve 90% substrate conversion. So if 90% are being converted inside the chemostat, only 10% will be remaining, which will be coming at the outlet, right? So the S0 is equal to 10 divided by 100, which is your 0.1 into your inlet substrate concentration, that is 14. So the outlet substrate concentration is going to be 1.4 gram per liter. So what we have to find here, we have to find what is the feed flow rate, what's the flow rate that we are using at the outlet, right? We know the monad equation, like Michaelis-Menten equation, like mu is equal to mu max S divided by Ks plus X, right? And we know that mu is equal to D. As it's a chemostat, we have already derived, and then we have seen that mu is equal to the dilution rate here. So if you substitute it here, D is equal to mu max into S divided by Ks plus S, and substituting the values, you will find out what's the value of D. So D is equal to 0.264 R inverse. And what's the formula to calculate dilution rate? Dilution rate is equal to feed rate divided by volume. And rearrange it, you will have flow rate is equal to your dilution rate into volume. Dilution rate you have found it here, and you know the volume. By multiplying both, you get 11.88 meter cube per hour. And the answer closest to ours is A, 11.9 meter cube per hour. Okay. Moving on to question 7. Sulfate oxidation method can be used to roughly estimate a volumetric mass transfer coefficient, which is called as KLA. Dissolved oxygen mass balance E. So the sulfate oxidation method is mainly used to like if you guys have gone through the B3 video, you will understand that there are two ways to estimate like KLA. One is through your sulfate oxidation method, and the second is through dynamic method. So here in sulfate oxidation method, what happens is that sulfite is going to get your sodium sulfate is going to get converted into sodium sulfate in the presence of copper sulfate. Okay, so what they do in this experiment is that the sulfite is being like dissolved and kept it in a bioreactor, sodium sulfate, and the dissolved oxygen will be like through the sparger, the oxygen will start entering the reactor. So whatever the dissolved oxygen that is being present in the broth, that will react with your sulfate in the presence of the copper sulfate that you have already mixed along with your sodium sulfite. This will help in producing sodium sulfate. So if by plotting the sulfite concentration versus your time, you will be able, from the slope of the curve that you are going to get, you will be able to find what is the KLA. Okay, so the right answer here is going to be KLA. It's not dissolved oxygen. We are not going to get the mass balance. We are not going to get the yield from this. We are just from the slope of the sulfite concentration versus time, we are going to get the slope as KLA, which is nothing but the volumetric mass transfer coefficient. Moving on to question 8. Identify the device used in aeration flow rate measurement in a bioreactor setting. So they have given baffle, either rotameter, RTD, and tachometer. So like baffles are going to be, here baffles are there, which are going to prevent your vortexing inside your bioreactor. It's not going to help you in measuring the aeration flow rate. Okay, and rotameter is here, through which we'll get to know what LPM, that is liters per minute, we are going to send air inside the bioreactor. So rotameter is the right answer. Rotameter will help in adjusting what is the LPM, that is your liters per minute of oxygen or air that you are going to send inside the bioreactor. And RTD is nothing but resistance temperature detector, which will help by changing. If the temperature is decreasing, your resistance will also reduce. If the temperature is increasing, your resistance will also increase. Based on this sensor movement, as this is directly proportional, your temperature will be measured through RTD. So RTD is not for aeration flow rate measurement, it's for temperature. And tachometer is used to find at what speed your motor is rotating. Your for example, your shaft is here, right? So your impeller is rotating at what speed, that you can tachometer will help in identifying by connecting it to the motor. So tachometer is also not for the aeration flow rate. So the right answer is rotameters. Moving on to question 9. Match the following microbial categories in A with their optimal growth conditions in B. So thermophile, cycrophile, and mesophile. So thermophile, the name suggests that it's going to be in a thermo, which is temperature, right? It's going to be in extreme high temperature conditions. So which is like extreme high temperature conditions here, which is your 45 to 80 degrees Celsius is for thermophile. Okay, phile is nothing but loving. And we know cycrophile. Cycrophile is exactly opposite to thermophile. It is going to love the low temperature, right? So which is going to be 0 to 20 degrees Celsius. Whereas mesophiles are nothing but which are like ordinary room temperature. In that range, they can easily grow. They love to grow in such conditions, which is like 20 to 40 degrees Celsius. So out of this, what is going to be the answer? B, where thermophile is 45 to 80 degrees Celsius, psychrophile is 0 to 20 degrees Celsius, and mesophile is going to be 20 to 40 degrees Celsius. Moving on to question 10. If the substrate concentration S is very much greater than Ks, then which of the following is true according to the Monod model? A. The organism grows at its maximum specific growth rate. The specific growth rate of the organism decreases. The specific growth rate of the organism doubles. The organism reaches stationary phase. So we'll just write the Monod model. Mu is equal to mu max is divided by Ks plus S. Sorry, it should be total. Okay. Mu max into S divided by Ks plus S. So here what they are asking, S is very greater than Ks, which means Ks is going to be very small and hence it's negligible, right? So by removing as it's neglected, what it becomes, mu max into S by S, and S and S will get cancelled, which is equivalent to mu is equal to mu max. So the organism grows at its maximum specific growth rate. So this is the right answer. Okay. So shall we discuss the queries that you guys have? Any questions out of these 10 questions that I have discussed? Is there any question that I have to repeat one more time? Anyone? If there is any question that I have to repeat.
Hello.
Yeah. Yeah, Mr. Gokul Krishnan.
Yeah, I have a doubt regarding the proctored exam.
Sorry?
The exam which is going to be conducted.
That I have no idea. You can email to the email ID in which you are getting this link, right, every week for the meeting. That you can
Yes,
ask, I
yes.
guess.
Fine. Thank you.
Yeah.
No, I just want to know whether it will be MCQ or will it be the questions to be answered like that, how it will be.
As far as
So
I
that.
know, it should be MCQ. Anyway, you can confirm with the concerned person one more time.
Sure. Thank you.
Welcome. Anyone else? Any doubt? Okay, if there is no more doubt, I want to end the session. Thank you so much for joining. I hope whatever we learned in the total. Yeah.
Yeah, and one more, I had a doubt.
Yeah.
In the assignment 2, what is given, there one answer was for the enzyme that uncompetitive inhibition.
Okay.
The answer was repeated twice. Both Km and Vm will be modified in uncompetitive inhibition. So same was given as the choice for C also.
Okay. I have to
And
check
I have answered the
question.
both.
Okay, you have answered the both.
This is in the assignment 2.
Okay.
But it was taken as wrong. The answer is taken as wrong. But which is the option was the same for both B and C.
Okay.
So how it will be taken out?
So
I just want.
can you send an email to the same email ID about this query also, because I'm not handling that part. You can send an email.
Okay.
They'll definitely help you to sort it out.
Sure.
Yeah.
Okay.
Okay. Okay. If there are no more questions, we'll end the session today. I hope whatever the tutorial that we have seen for week 3 will help you in solving the assignment 3. We'll see you guys next week. Thank you so much. Bye.